Professor Schnitzer, and I'm the resident environmental chemist here. And I really love the centerpiece. Thank you. So, ballpark estimate. How efficient are solar cells today? Any ideas?
They just reached, what, 45% solar panels?
Wow.
I was going to say like,
I think-
about that limits.
Yeah, that may be a super new.
Yeah, that was just reported.
That's amazing. That's great.
Or 42%.
All right, so we're improving over the years. I have to say, when I first started here, the textbook we used said that solar cells will never work for energy. And because it just took too much energy to make them, and their lifetime was not that feasible, not that long. But anyway, I mean, on average, 15% is where we're at, and obviously we're improving, so that's a good thing. But when I get excited about when you say 45%, you can see where we're at in terms of efficiency. So the beauty of photosynthesis is it's efficient. Efficient in the sense that for every photon absorbed, at least for the bacteria we're studying, 100%, nearly 100% goes on to the reaction center. So learning from nature how to be efficient and extremely fast. These energy transfers happen on a femtosecond time scale, 10 to the negative 15 seconds. So there are more femtoseconds in a second than there are seconds in a human's life. A lot, very, very fast. So this is something you may have memorized in middle school. And for those of you who've taken Biochem 2, you know it's a lot more involved than that. But what we get excited about is it's a way to get rid of CO2, a way to store chemical energy. And that really makes us excited, because then we can store it and use it later. And that's what we humans love to do. So think solar cells when you're thinking of storing energy. So this fundamental process of nature, photosynthesis, still has a lot of questions remaining. And that's where our research comes in. So, and I say our research, I collaborate with Professor Mehran Gunawardena in the physics department. And so we study photosynthesis in the sense that instead of using the sun, we use lasers in our lab. We have a laser lab, and we're looking into what we can learn from nature about photosynthesis. And in particular, the goal is to understand energy during photosynthesis. So what do we mean by energy transfer? Here's the light harvesting complex, LH2, that we get out of the purple bacteria. And when I say we, I really mean our collaborators at University of Connecticut. They give us the light harvesting complex, and which is fantastic because we are not biochemists in our group. And so it was hard for us to treat. We tried, and it was very hard for us to do that. So we have the sample from them, and what happens is when sun shines on this, it absorbs the photons and, as you know, rapidly transfers the energy in the form of electron transfer to the reaction center. So how does this energy transfer occur so fast? And so there are two schools of thought here. There's a semi-classical view which says a pigment molecule absorbs the photon, excites it, the electron transfer happens in a hopping fashion to the reaction center. So the electron hops from pigment to pigment, looking for the lowest energy state. The quantum coupling view is this idea that when the pigment absorbs the photon, instantaneously it sends out its feelers, and in a coherent energy transfer way, the electron exists in two or more states simultaneously. And so by doing that, it could identify the lowest energy state instantaneously. What does our lab look like? It looks a heck of a lot like that. We have a laser table, which is literally a table that has all these holes in it that we screw the optics into. This is the heart of our system. That's our femtosecond laser. We have to tweak that quite often to get the energy up. And although it looks like it generates green light, we send green light into it, we're actually looking at the red infrared light that comes out of it. And so this is up with the lights on. That's our laser table, and just like a mirror steers light, reflects light, that's what we're doing here. The light comes out of the femto just like a laser, and we just steer it around the table to do what we want it to do. And that's what you would be doing on a daily basis. You would be working with this, that'd be 1 minute, working with these optics, and and so we want people who enjoy this kind of working with your hands, tweaking, and that sort of thing. So we're looking at energy transfer, particularly optimizing right here this 0.8 picosecond transfer. And we do a pump probe experiment, which basically excites the sample and then I'll take a picture of it as it relaxes back down. And here are the members of our group. Professor Gunawardena is in Sri Lanka this year, but hopefully he'll be back to work with us. And here are the rest of the players, and that is the end of my talk.